Hello, friends. Are we there yet? Is it where? Oh, shit, this is loud. Oh, wait, I didn't. There. Wait. Oh, that's too loud. Huh? What? So much going on already in the chat. Hey, Adam, Ray, Taurus, Tech, Aaron, M40K, Ray, Johnny, Christian, so many people. What's going on? Louis is there. Rota, René, Anna, Daniel. What? Bicycle helmet. Ah, yeah. Hey, Daniel. Why? Why do we have so many people? 2 minutes warning? What warning? Oh man, Christopher, hello. So many people. What's going on? Option 22 seems to be very convincing as a topic. PCB design? Yeah. Okay, so I need, so we have not easy EDA. I will be using KiCad. I think so, at least, for now. So I will use KiCad. I can do also easy EDA, but I'm not sure. Where's my Tang Nano? Oh, here. Yeah, FPGA. So I have a sponsorship going on, and I started using FPGAs as well, and that one that's like below 20 or $20, and it has 9K LUTs, some SRAM and stuff like that. So it's quite a capable one, and it has HDMI as well. So the board itself. So far, I only managed to upload examples and modify the examples. So fried programmed garbage. Yeah, so I have a monitor here, but I didn't manage to. One of the possible topics today would be to manage to. There is an example for this board. It's a RISC-V system on chip with HDMI, and you can control pins over serial. So that's basically like an example code. And one option would be to take the HDMI implementation, extract that, and just display a sample image. That would be a good thing. Then another Hey, JK. Another project, last time we managed to use the face tracking, or the face detection is focusing always here. We managed to use that to inject into the memory. Still, it's quite slow and a little bit buggy. And what I discovered, let me move that up here so I'll be more looking in the direction where the camera is. So I checked again. I have no clue why I didn't take the ESP32S3, because the S3 has enough pins to not use shift registers for the addressing. So the addressing, setting the address takes a lot of time. And also I want a mechanic that, so one thing that's happening right now is that we write a byte in this, let's say, register, and address into these shift registers, and they are disabled. And whenever we set output enable low, because it's an inverted signal, they will output this to the C64 at the right clock. It's like, but what I would like to do is to have it only output for one duration of one clock cycle, and then disable for good. So as soon as I give it, like, from the ESP, okay, output that data, it should basically set the output enable at the right clock phase, and then disable for good until I trigger it again. So that's a logic that I want to implement, and I want to make a PCB for that one. But I want to do it for the S3. I hope that that works right away with the S3. I think, yeah, we can just take a board. Yeah, we can. I should have everything here to make a S3 board. This is the S2. S2 is no good. So we can design an S3 cartridge, but then also I'd like to. Yeah, that's the plan. Okay, so let's check out what we can do with the signal. So it's some kind of latch or flip-flop that we can use. You're interested? Exiler? Okay. Yeah, that's the Tang Nano 9K. Checklist? Oh, okay. So what do we start with? Where is the fondue? There is no fondue yet. Okay. I would design the board first, and then I can even show you what the Tang Nano does. So let me check. Can I share that? I can share the screen. Let me share the screen. Not doxing this time. Screen capture. Bloop. Yeah. So this is the code, but This is like from the manufacturer of the FPGA, GoWin. That's the EDA. Yeah. This is like the example with HDMI. It's quite complicated, so I might just open a different project. That one. And it's quite simple. So we have to like learn Verilog to do this. So this is design, easy design. So this is the language you don't do. Can I zoom in somehow? This is like mini font. Can I size? Whee! Okay, now you can read this. So this is not like code that's sequentially running. You basically define like modules. So this is like a definition for the module with LEDs that will access the onboard LEDs. This is the end module, and in between you define, let's say, a register that would be like stored in an intermediate. Where's my face? Where's wait, do I have a here? Okay, so that would store like the output, or this is the counter, so this is like stored in flip-flops, the bits, and you have something that's running always, and then on a positive edge of the system clock or the negative edge of the reset input, it does this thing. So okay. Okay. Yeah, so so again, yeah, register stored in flip-flops somewhere on the logic of the FPGA, and then you basically define how it's wired. And in this case, you want like that this will be always active, like this will be always triggered by a positive system clock edge or a negative edge for the reset. Because yeah. Oh, I'm so sorry. Okay. So I think the button is like always high and you pull it down when you press the button down. So that's why when button press is detected, which is basically in this case the signal is 0, so ground, we reset our counter, which is that's interesting. So you always specify the count of bits. In this case, you have 24 bits from 0 to 23. And when you specify like a number, you say how many bits, then the radix. So in this case, it's a decimal, and then the number, which is 0. And if you have a notation like that with an underscore, the underscore is ignored. It's basically for your visual. If you can maybe split it, if you have like a bits definition, like here, this is a 6-bit number with bits. you can split it by 4 or whatever with an underscore. So so what it does is every clock cycle oh, is it? Wait. No, it's not anymore. Metaverse is getting legs. Okay. Okay, so so this is like a reset of the counter is done by this here, and the positive edge of the clock is basically triggering whenever counter is lower than 24 bits, and then this is basically the number because we have, I think, 27 megahertz clock. This is like half a second. Yeah. Oh, really? Nice. Yeah, I'm just getting familiar with Verilog, so that's why I'm rambling here about Verilog. But it's fine. I would use Verilog over other hardware defining languages because it's similar, like from the syntax is similar to C. Yeah, and otherwise it's just reset. And what's happening here on the positive edge of the system clock, what's happening here, a reset is the LEDs are also tied high, so a low bit basically lights up a onboard LED, and it resets the LEDs to this state. And basically, whenever the counter reaches half a second, it moves the. So this construction is interesting. So you basically put the fifth bit, so the state of the fifth LED to the state of the first bit, or bit 0, and then shift everything. So it's just rolling the one lit LED across everything, and that's basically it. Otherwise, it's doing nothing. So, and yeah, we can synthesize root and place. I don't know if we can. I think, yeah, there is a lot of stuff. I think there was some net list. Wait a second. There was floor planner. Okay, I have no clue how that works yet. We can take a look at that, but yeah, it does something. So we can port primitives nets. I don't know how that. I'm a little bit confused that it doesn't show like the routing or. Oh, interesting. Look at this. Okay. Okay, however, we can just program it, but we can't use like the regular programmer. We have like to use a alternative programmer because that uses USB. And I will just plug it in. Do I have a longer cable? Let me use the longer cable here. Yeah. Oh, You are doing manual floor planning? Really? Okay. Here, let's upload this. I have the you can do different stuff. It has even like programmer not available. No. I just, oh wait, that's the wrong code. I have basically specified the project here. Oh, I flashed the wrong project. This is the right project. You're right. So since this is an external program, I have to specify the byte code here, and basically there is also, you specify what you want to do, because there is also an SRAM mode. You upload the code to the SRAM and it will basically run until you unplug it. Okay, however, I don't know if you can see. Let me switch it. Here you go, easy peasy. That is FPGA for you. Check, next one. Okay, let's do something. Let's change the code. Let's change the code and see if we can do it. Let's do it like, let's spend less time. 10 times faster, Rara. Okay? 10 times faster. And what else do we do? Let's leave it like that. Let's synthesize and see if it's, yeah, it's done planning, program the device. So the problem with this programmer, the built-in, this is like the educational edition. So I'm educating you now, so it's legal. It basically, it can't detect the device and whatever. I don't know why that doesn't work, but there is an alternative programmer on the side of you can download from SciPete. Yeah, SciPete. SciPete has a wiki where they linked like the other programmer. So let's upload using this programmer, and then we should see a faster Blinky. No, that's not a faster error. Wait a second. That didn't work. Wait, what? Why isn't this faster? Huh? What did I... Wait, am I the right program? Wait, did I upload the right one? That's the right code, isn't it? Huh? No, this is... No, that's... Maybe I didn't save the code. Wait. Oh, yeah, code not saved. Here we go. Okay. Oh, sorry. I didn't save the file. You didn't see it, but I'm uploading right now. Okay, here we go. Woo! Okay, so So this is FPGAs for you. Easy peasy. And there is an open source tool chain. Let me check the open. Oh, do you want to see how VGA looks like? Let me upload this code here. I'm uploading. I upload code. Yeah, unused until you want to do like HDMI and super fast ADC reading. So okay, there is like an intermediate step that I want to share. So I uploaded the tiny Pico core, which is an RISC-V. Okay, so the problem is now, is it on? I hope I have the right one. I must check if I have the right firmware again. Floor planner, no. So let me open the file. Pico tiny pro. Yeah, I changed stuff. I changed stuff, so no, it doesn't work right now. Okay, let me check. So I think I changed the. No, that's the right one. Yeah, it's a ton of warnings. Still TMDS stuffs, yeah. It's plenty of stuff, and it uses an open source implementation for HDMI. Yeah, let's take a look. So SVO, you can find this. So if you look for Clifford Wolf, yeah, he basically published on GitHub like an implementation for HDMI. I have still to like analyze it because I have no clue how the memory is used or implemented. I tried to where is the specification? There is you can set different resolutions, but I tried full HD and that didn't work. I think I have to re-upload. I'm not sure why I don't get. Yeah, these here are using resistors, not caps, I think. But I have no clue why it doesn't. Ah, that's show effect. Oh, they can push even more. I don't know. There is a specification, but oh, maybe we don't have a clock that's high enough for yeah. Hmm. Let me check if it's running. We can use we can use the Arduino thing to see if we can change the LED states, which is basically yeah. Oh, that's why we can't reach higher resolution than that. This one is yeah, so this one is clocked like by the main clock is 27 megahertz, but I think you can do different stuff with PLL clocks internally. I have no clue why. Okay, I don't know why this doesn't work anymore. It should work because oh wait, it wasn't plugged in all the way. Here we go. Okay, it has the user interface and stuff. I didn't plug it in properly. That's the show effect for you. But I mean, this is like a full implementation of yeah. That's like a full implementation of a rookie mistake. Cyclone 3 and Cyclone 4. Okay, okay. That might be the issue. Okay, this is like I think this is even the lowest resolution that we can do. What's happening to Apple? Should we try different clock? So wait, defines. These are all the resolutions that are supported, which are plenty. I think HDMI supports. That's interesting because usually that's not supported. So we have like line doubling or something. Should we try maybe? Oh wow. PayPal. Why PayPal? What did I miss? Okay, so what I want. What? No good, huh? Okay, maybe we can use a resolution, half the resolution or something. I would like to use like full HD because that would be supported by. Oh yeah. $960 by $540. This is half the resolution. Maybe we should try that. Should we try that? PP account. Yeah. They are already like taking, if you like do currency conversion, it's basically random. It's not transparent what they take like as a margin for currency conversion. It's certainly not Forex. It's certainly not Forex rates. And that's a problem for me whenever I get paid on Patreon or PayPal donations in different currencies. I pay around 5% for the currency conversion on PayPal, on top of like the other fees that I pay, whatever. And there is even alpha. Okay, that's interesting. Should we try this mode? Oh, food of the day. Lebkuchenherzen with filling. But it's so sweet, I'm really like, ugh. What's about Mac? What? Okay. Is it done? Yeah, it's done. Okay, let's try to upload it. Oh, what? Wait. Wait. Did I not store it again? Oh yeah, I didn't store I didn't store it again. Is there a setting for auto save? Behavior. Now we have to wait again. Synth project. What's synth project again? Oh wait, this is okay, let's do option 22. FPGA is done. Change resolution. What? What? Okay. Change resolution and the other stuff we can come up later with, okay? Let's continue with the upload feature. Yeah, I'm happy that I even got it. Okay. Not worky. Not worky. Is there a V? Is there a V even? Oh, wait. I don't know what the V means. Or R. What is R or V? There is nothing there. Do we have like, what is this, 480? 480? Ah, but I need another 480. 480 by, yeah. No, but there is no, I want a 16:9 resolution and I can't get it. I don't know why it doesn't show it. It might be like with the test screen or something hard-coded in the firmware. I can change the firmware. I would have to install a RISC-V Eclipse IDE to compile new firmware that we upload on the FPGA RISC-V. So the bytecode that we upload using this uploader here, this is like a Python programmer that uploads a new code to the FPGA, to the soft core. But this is bytecode that's already compiled. And I tried on the Hangout, I tried to download this IDE and oh yeah. Yeah. WSL, I want to. Okay. Do we have another resolution here that we can use? Wait, there is 60:9. Okay. I think this is hardcore for you. What? Okay, we will do this PCB design. Let me just try. I'm also really new to FPGAs. I'm completely new. I think this won't work because HDMI doesn't support this resolution by default. Either if it's pixel doubling, some hard-coded pixel doubling. LCOS projector, what? Ash, what did I miss? I should check out what you're making there. That's good. You use resolution. The problem with all the socks is that there are so many, like everything is a new platform. Like I would love to work with the Pi Pico and also with the ESP32, but my capacity of my brain isn't like high enough to memorize everything. And I think working with FPGAs at some point might be the solution, because you are free to use the same stuff on any FPGA almost. What? Really? Few dollars LCOS? That sounds interesting. Wait, did I upload? Oh, my VGA library. Oh no. Did I upload it already? No, I didn't, huh? Yeah, fake HDMI won't work here. I will have to revert to... Nah. Nothing. Nothing. Okay, that won't work. Beeps. See how defines. Wait a second. Wait a second. Oh. Wait. Why do we have like two definitions? This is HDMI, SVO, HDMI top. Oh. Uh-oh. 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 I should use same definitions in both parts here. Okay, let's try again. Let's try again. I will try again with 720, 1280 by 720. Where is it? This is like HDMI ready. That should be like HDMI spec. Okay, you know what? Let me try that, because this is, unfortunately, I just saw that there are two defines. Wait. And I hope that was the error all along. Okay, it's... Yeah. Okay, that didn't work. Ah, okay, my friends, I give up setting new resolution. That didn't work. Let's continue with the other stuff, huh? That's still up. Why is this window so huge? Why is this window so big? I'm resizing a window today. Yeah, this is when you work on a 4K screen combined with only HD screens. It resizes all the time. Okay, fuck. Oh no, it resized again. Okay, okay. Yeah. Text, okay. Okay, didn't work. Change resolution. Okay, next is I have like I show you my setup of screens. But the problem with this setup is this screen and this screen, they have different resolutions. All the screens have different resolutions, so it's all over the place. When I move a window like between those two windows, it's terrible. Okay, so that's okay. Okay, next is we need to define the logic for single clock logic. Okay, single clock write or even read logic. Single clock logic. I don't know if I need like write logic. Read. No, read logic is. Read and write logic should be the same. Okay, single clock logic. Then we need also, lab. I would say go to lab and discuss. Yeah, use lab. And then design to S3 to S3 board. Yeah, that's it. And that oh, we covered already how to work with FPGAs, programming them. HDMI output was covered already, and this within 1 hour. we Okay, so far in the first hour, we had started with blink LEDs on FPGAs, then moved on to HDMI, RISC-V softcore, programming the softcore with Python. Yeah, and now we are moving on to Paint. No, oh, that's the wrong Paint. That's Paint.net. Ah, close it. That's too sophisticated. Paint. Yeah, I love to share what I learned. So, okay, let me dig out our stuff that we did last time. That's in C64, and we have this logic here. So yeah, the actual fun part. Okay, so everything's confusing. Okay, so when do we write? When do we? So this is not output enable. So enable equals NAND of like phi2 and this is now E output enable. So this is now oh shit. Okay. Let me fix that. This is about the C64. So we made this board here. I okay. So this board writes to the memory on the bus. Ouch. No. No, that has nothing to do with the FPGA board. It's a completely different project. It's basically, this is option 22. Option 22 is about all the cool stuff. Oh, by the way, yeah. I will show the PCB. By the way, this is the project that I made, like my fume extractor with the Tesla filters. I made this. Look at that Tesla filter, HEPA filter with activated charcoal. I had to cancel the video because the laser was like so toxic. I couldn't like recommend it with like a good feeling to everyone. Stupid. Okay. Yeah, full screen board. Here it comes. Request. Full screen board. Okay, so this rat's nest, it's fully functional board. This is basically an ESP32 board with, this is NAND gates to calculate what we saw here with the output enabled. This is like a buffer for the data, 8 data bits that we push to the bus. And these are shift registers, 595 shift registers with the 16-bit address. And then we have some other logic like read-write to pull stuff down, some resistors to protect everything, pink LEDs and such. And this is, maybe you can see the labels. Yeah. No 245s, it's 595s. Okay, and this is basically a cartridge for... Yeah, so that was that. And the problem is that we were able to write to the keyboard buffer last time, so this still is implemented. Now, yeah, that's very smart. That's very smart. What we did there is we did to not interfere with the VIC controller. We did this. So the phi2 signal is basically if both are true, so our output enable signal from the ESP32 E output enable and phi2, if they are both high, then that's that's an AND. Then when we enable the output of the address and the data bits. So we can only use like, yeah, it takes turns. That's true. So we are only allowed to access it during this phase, high phase of phi2. Okay? And this is when it's okay for us to write. Okay, I think that was it. Let me check. Let me check again the specs. Let me check that. Yeah, I have the docs somewhere. I stored it. PCB. Where did I store it? Huh? I thought let me check the... Okay. Output enable. These are our other signals. I can't find where I stored. I think I had, oh wait, no. Maybe I just saved the address. So let me check. Yeah. No, that's open card. That's something else. Okay, whatever. What I need to ensure is, so now we have to... So what the problem now is, that what we have is we have sometimes like errors, and also we have like we are increasing the chance of an error because we're changing that at a random time because we are not in sync with the clock here. So that might look like this. And then we basically, what the result will be is then this, then this, and then whatever. And what I want to do is I want some kind of latch or flip-flop or whatever that it's basically it's triggered once and then it's done. So I want to write for half the clock, I want to write at the correct phase, set the output enable, and then disable again. So we have to write some logic to do this. So you have returned with snacks? Okay, so what we want to do is we want on this edge, we want this here, and on this edge we want this here. So the best thing would be to put something in between, like E output enable. So if we have something that's basically disabled by this or reset or something, that would be the best. So whenever the clock goes low, it will be then reset and we would be done. But we have to wait for low phase first. So how do we do this? Let's take a look at some logic stuff. What the hedgehog crossed the road? Okay, or let's think about what we want. We want that remembers me of also the same like writing Verilog. So when phi 2 is low, phi 2 low, phi 2 low, EOE, EOE is high, then we want X be assigned high. D flip-flop. AOE pre. Wait. Okay, let me just write down the test case. Okay, I'll come back to this suggestion. D flip-flop. What is previous? Yeah, you have to like wire it back, but then we have to delay it by the clock or what? How do we do this? Okay, let me write this suggestion down. Okay. Then when oh, you know what? We don't. We just write a logic table. So when this is and this is yeah. But will it keep it? Yes, yes. Phi 2 is our clock. Okay. Let me check again. So when we have, okay, in the case that both are high, so we have high and then high, then okay, and then we need, what happens if we have high? this will get interesting. Yes. So this will be then to avoid metas. Yeah. So what I want to do is like this is like off. You can see it there. It can happen anytime. It can happen in the middle of high. So we need to assign X during this phase here, during the low phase, and then basically output it whenever we have a high clock. And so we ensure that we don't assign anything at the end of the cycle, which wouldn't be sufficient to write correctly to the memory. 90%. Yeah, we had somebody wasn't a mod yet. Adam, why is Adam not a mod? Adam is mod now too. Usually all people that I see not for the first time, so everyone is able. I mean, Michael, you need to speak up more often, and if you need to drop a link, tell me, you will get a mod rights. But you're not the first time here, Michael. No, okay. Yeah, but we can do the same like on inverted clocks. So, and what happens here if both are low? Both are low. Oh, we didn't assign this yet. So this will be, wait. Yeah, wait. So this is the high phase. Shit. Yeah. This is the new thing, but how do we? Okay. This sets it low. But how do we synchronize EOE before? We just need to end it, but we need to avoid. That's what I'm trying to do. What do we do in this case? Phi2 is high, and this is low. Yeah. So we don't change. That's easy. Look at this. Look at this. Super easy. We don't change anything while phi is in the high state. We only change it in the low state. Oh, but then after it's low, we need to, oh, wait, there's something missing. Oh, no. Once it was high, no FPGA stuff. We moved on already. Okay, whenever we assigned, no. Oh no, oh, we need like, oh no. Okay. Daniel, XOX, Kata, what? Okay, we need something like Y. Oh shoot. No, that's okay. Let's start again. Let's let's start again. No external interrupts. Okay, so I have no very okay, and this is how this will be X. Okay, we need a longer logic table because it depends on this before state, okay? So before state, yeah, you can test it. Okay, let's start with that. We have truth table here. Then, okay, we were done with writing. So X is 0 and phi 0. Oh, this is also how we can keep the things here. Wait, let's do 0, no. Yeah, do you think so? Oh, why do I do one like that? This is nasty ones. Here we go. Okay, so what we learned is, let's assume we have nothing assigned yet with X. So we don't do anything when we do everything when phi is 0. So we assign 0 here and 1 here. Oops. 1 1 here. Oh, we don't do anything. We change nothing here. We change nothing here. Then zero tolerance. It's 2 clock domain problem that need to be synchronized usually with 2 flip-flops. There is a tutorial that I scrambled across some years ago from an engineer of Xilinx, and I think was. Do you have a link for that, tolerance? You can, I will put you moderator. You can drop a link if you. No, this will be hardware with logic gates, with NAND gates. I have FD flip-flop also. So we can use flip-flops if we want. Okay, now what happens? So when phi, oops, yeah, you missed that. No, wait. When phi is 0, x is 1, we set it to 0. Then when phi is 1, we don't do anything, do we? We keep the 1. This is our logic. Solved. Edges? Nobody needs edges. Do we need edges? Yeah, no, we take care of the edges with this one. So we will basically replace that by X. And our output enable will be synchronized with phi 2 with X. And since we are more or less no. Yeah, this we had this. This is not what we want. Okay, this is what we have. This is what we have. These are our this is ESP32 signal. This is the clock of the C64, and this is our output. This is what we have on this board right now. Yeah, but the problem is that it wouldn't respect stuff like if this signal would start. Let me do something like that, like edge cases, where the signal would start somewhere here. like that, we would have a signal that would look like here. Okay, and we have something like this here, which is really ugly. And that causes errors. What we really want is something like that here. This is our new output enable. Yeah. And this is what's happening here. It's similar to, I mean here, it's similar to a flip-flop because the output is also, oh no, oh no. Wait. I have to check. I have to check if this also covers, if this works like a flip-flop. So if we switch the X in these cases here where the X changes, if the X would affect the output. So we need the same output at 0, 1, no, foo. No, this is, yeah. You are free to link an explanation yourself. Okay, we have the problem, the switching signal. What happens with that one? That switches to 0, which this is okay. So this is okay. This is okay. This is not okay. So this is the problem. Now I need to find a logic table that will stabilize. Edge triggered logic, but this is edge triggered, more or less. Am I wrong? Am I completely wrong? If you have this feedback, we just need to avoid this oscillation here. So this is an oscillation, and yeah, it probably we need a flip-flop in between. So this will be like x2 and x1. Shit. Oh, I need both? Really? I think I this is ah. Okay, let's see. RS latch is not enough. You say RS latch? We need the D flip-flop. Let me check. You know how long ago it was that I used D flip-flops? I had this in university 20 years ago, more than 20 years ago. D flip-flops. Yes, here. This is what we want. And this is what we get. Like the black lines is what we get. Oh wait, these two are our inputs, and this is what we want. DJKRS flip-flops, yeah. all these old flippy floppies. Oh, that's clock. Here we logic. Wahrheitstabelle. Yeah, it's long time, huh? Oh no, why is the internet so broken? Yes. Look at this. This looks quite similar to what I want, except I want this be gone. That's an RS latch with an inverter here in between, huh? No pin interrupt. Okay, I tell you why no pin interrupt. Pin interrupts are staged. If it's working on the Wi-Fi, which has the highest priority, it won't trigger at the right time. We're working here at about 2 megahertz then. Invert C. Yeah. Okay, so clock. So this is our output, which is basically, it's inverted, but this is what we want except for the second. So how about we put how do we do this? PI, the solutions. Yes, I will hit you with the hammer. Suggestions. It's like being on an internet forum. Why do you want to do this in the first place? I'd go with that too. Yeah, you do it then. You show me the result, please. Next week. You have time until next week. Okay. So, how do we return this is staged? Okay. I might have an idea. Okay, let's do it the lazy way. Okay, here we go. Yes. Yes, that's what I want. Art and RS. Yeah, so this is what we get. This is our, let's start over again. Input, We have clock. Okay, then we have what? Falling at. Yeah, try to draw it. I'm trying to find a good. Okay, this is our input signal. This is what we want. And oh, wait. This will be, this makes it even more difficult. So this is our example. So this is what we want. So in, and this is out. Stupid color. Yeah. After the high, I want one pulse. This is okay. That may be the easiest explanation ever. Whenever we have rising edge, we want this here. So this is rising edge on low, which is, or here is a rising edge. Okay, rising edge, and then on the next rising edge. Okay, so here, this is rising edge, and this is the next rising edge. This is what we want. Okay, let's write down, this is, I call it P, okay? P, and this is E, and this PE, and this is X. Yeah, this is the label. This is P, E, and X. And then we have, oh yeah, maybe I should also mention that, yeah, but this is clear that this is falling. So this is falling and staying there. Okay, so this is clear. We can do some intermediate signals. So what intermediate signals do we want? We need like an intermediate signal of this rising edge here. On the rising edge. Wait, E equals P and X on the rising edge of what? Of P. Rising edge. Arms one shot. Okay, so we need a D flip-flop, but wait, it's more like an RS latch because we don't want to use any clock for that. Doesn't it just look like high on E during a clock pulse? Okay, so here is the also one important detail that it stays, so it's not just an AND because it stays armed and then it's disabled also. So hey, Mr. Sion, do you want to theorize? Sorry, I couldn't find any more about your needs and your firewall state of flip-flop, which is enabled by an enable and only reset to the falling edge of phi. I try to understand the sentence. I couldn't find any more. Yeah, okay. So let's try different stuff. Let's take a look at an RS latch, if that helps. RS latch. Okay, yeah, we can do that. So this is P. Oh, wait. So we have P. Oh, wait, we can basically do dot E, which will be then oh. Okay, this is what we get there. Okay, this looks a little bit odd. Erect. What? Root canal? That sounds painful. Yeah. Alberto, so we are trying, this is the input, you see the inputs and the output. This is what we try to do. And we need to do it with logic gates, or maybe a flip-flop, or RS latch. JK flip-flop, how does JK look like? Latch, toggle. Oh, that toggles even. Oh no. Okay, I don't know if this helps, but how do we decide a rising edge? On rising edge. Let me check that. On rising edge. No, the HDL doesn't help because we need to do it in hardware. Flip-flop clock decides rising or falling edge. Set and clear then used with other logic. Wait. Okay. Okay, I checked the lab channel. Let's see. Let's do. Oh no. Okay. Let's take a look. No, I have all the chips that we need. Okay, you know what we can do? I mean, to simplify things, we could also do the following. Okay, this would be for the time being. If it's way simpler, we can. This is an RS latch. How do we simulate that? Okay. Let's draw the signals first. Okay, let's draw the signals. Doing it with paint is now paint in the ass. Okay. P and X. This is, oh wait, P and X? Oh wait. P and, wait, what? Hä? But X is output, not input. Where? Which? Wait, what? I'm confused. Okay, wagon loads. X is output. So where do you use E in this case? Okay. P and X and EOE toggles X. P and X is X. Okay, now we have Chris. We have a nice mix of stuff. Alberto. Okay, X is E and not Q, with Q from a D flip-flop with E as input. Okay. And okay. That's but the D flop flop. Oh no, I need to simulate that. This is, how do I do this? I need to simulate that. Flip flop is never fun. Flip flip. How do we simulate that? Do we have like online logic gate simulator? Nice. Okay, here we go. We have a clock. Yeah, whatever. This is our phi. Then we have push button. This is our, okay. This is our D flip-flop. Wait, what is this? Why do we have a clear? Wait, what? E and not Q. Oh yeah. E, oh wait. Oh, what? How do I shift it? Oh, this is how, okay. I hope that works. How do I trace the signal, the output? This is, how do I do the output here? Okay. Wait, what? Where do E as input? This is, wait, the out of, oh, this is what we, oh, you can't see that. No. Oh, wait, this is X? No. Something's wrong here. I can't move this? Okay, here we go. Huh? Input of, like that? No. Huh? This is the input. Or what is the input? Is this the input? It's always on. Ah. Oh, wait. It's a fun tool, though. Wait, what is... Do I need to like assign, what is, this is clear? What is this, D? What is this? Previous? Let me get help. Load their demo. Latch. Yeah, but I destroy my file. Save it. No thanks. Don't save. Okay. No, there is no flip-flop use. Ah. What did you? Oh wait, this is. Ash. Ash. Oh no, positive edge. Negative edge reset. Oh, did you simulate that? Oh, there is a delay. What's happening here? Huh? What is? Oh no. Yeah, it's okay. It's okay. It's a bit delayed, but it happens. Oh wait, what is that here? What is that? What is this sabotage here? There is a sabotage here. What is this? Do you see the blip? This is where the problems happen. It's cool that I mean, I didn't do any Verilog until like yesterday, and now you're dropping Verilog code, and I can like understand it, what you did there. Okay, you have a 2 bits register here. So you have these are two flip-flops. Circuit lab, it's better. What is circuit lab? Where do I find it? Circuit lab online. Launch circuit lab. Let's do it. Starting. That's fun. That's fun. We learn about hardware now. At least some kind of logic level hardware. Not caring about analog stuff. Okay, yeah. How do I file new? Okay, here we go. Ah, wait. Yeah. So, wait, that's very sophisticated. Where's the D flip-flop? Here. Half adder, full adder, adder. Oh, there. RS latch, JK, D flip-flop. Okay, here we go. Clock. Digital clock. Digital value. Here we go. And you had an AND gate. What was, oh, I lost your, Okay, let's try again. X equals E not Q, so we need like that. Okay. ES input. And digital probe. Run. 1 megahertz. Okay, here we go. Simulate. How do I simulate? Run. How do I... Oh no. Can I do it in real time? Wait, I can't hear anything. Is TTS dead? Oh, okay. Yes, we can do this. Hey, wait. Huh? How do I build? Oh, here we go. Like that. Nice. Can I do like a random input or whatever? Ah. Okay. How do I get an input here for the simulation? Yes. Okay. And I will do it 1 point. No, this will be 0.3, okay, hertz. And then start time, stop time, 30 seconds. Time step 0. Error. Wait. Do we need to probe it somewhere? Like here? No. No. How do we simulate that? What the? Oh yeah, that's the output. Okay, nice. So what? What's the issue? It's like a super simple example. Are you kidding me? Are we stuck? I think we have to get back to... Okay, let me check the flip-flop again. Maybe we can do it in paint while this solver try. Anyone to? Okay, I sense that you people are trying to do it. Your circuit should not work. The AND gate has inverted inputs. Clear? Please drop it in lab next time. Not on the rising edge of phi, on the rising edge of... Yeah. Was it working though? Did I close the other one? Oh, fool. Did I closed the other one. Oh, here we go. Yeah, but what is this clear and the... And then wasn't... Did you solve it though? I need more input. Need input, Stephanie. Oh, we have a what is that? Okay. We have a simulation here. Ash. What is this, Ash? What did you do, Ash? What is this? Ah, okay, yeah. No worries. Okay, no worries. Okay. So, how about we use a flip-flop for E And whenever we get like this, it gets spoiled kids, really. Okay, there is another thing that we can try. One shot. Is there like, is this a standard logic? One shot, one shot, one shot, one shot. Please link something. Yeah, but one, you can use a NAND, not two NOT gates in between or something. Use 555. Okay, okay, how about we invert E, so we have something like that. And use the inputs rising edge. No, that doesn't help. One shot is delayed, you say. Something like, let me clear that. Phi and E. What is, which signal? Set the flip-flop. Okay, this is Phi and E. But then we get like, this is not a one shot anymore. This is the challenge. This is a challenge. That's kind of what I try to build on logic. Like I don't know how this this thing here, logic. What is what? Maybe let me check if we can find a similar D flip-flop with some extra stuff. How does their flip-flop work? Yeah, clear, but do I have a regular? Let me check that. My logic gates. Okay. Aha. Okay. So what is this? This is 595. This is not what I want. Wait. C595. Where's the D flip-flop? 7-4. What is 7-4? Okay. Okay, so this is a chip that I already have. Clear. I think I even have that one. Yeah. Gehäusebeschreibung. There is not even. Oh, there is no data sheet. Okay. Let's check Mauser. Here we go. Okay. Okay. Ah. Ah. Set, reset. Set, reset. And there is a clock. What? What kind of D flip-flop with set and reset? Is there like an example for... Wow. Look at the truth table. Yeah. I'm wondering if the truth table set, reset, no change, both are high. That might be quite useful with what we want to achieve. What is the star? Both outputs will remain high as long as set and reset are low, but the output states are unpredictable if set and reset go high simultaneously. So how do I disable set and reset? Do I have like a don't care value? Set let's ignore these states. Okay. Didn't upload yet, or do you mean? Ooh. Yeah, this one. And that works. Do you have a simulation of that output? Triple AND. That's yeah, but in the sim earlier you showed there was like there is a, first of all we have a delay by 1 clock, and there is this thing here. Do you see that? Do you see, like, there is this small blip on the output? This glitch. Especially like this short glitch can mean that the address is not still set properly enabled, but the data is, and it writes random data at some point in the memory. Or the address is like still the address that the VIC was accessing while the data is already writing. So that glitch is Can I make a suggestion? How about we leave that part open okay. Block 1 picofarad capacitor. Okay, I can do this on stream. But what I can do, because I can't simulate right now. I don't know how to simulate that easily. So what do we, P and E as set and P and not P as reset. Max, but what are the other one? Not peak and clear Q. You have the gate simulate using a breadboard. I could simulate oscilloscope and output stuff. Deglitch. Second ESP32. Use FPGA for all this stuff. Okay, I can make a suggestion. How about we design a board like that? Okay, let me draw it, since we want some PCB design. I didn't want to make a long stream today, but it seems... Okay, we make a board like that. Why isn't that a drawing? Okay. We make a board like that. That looks like that. Okay. It has the address. Okay, we have the bloop. And we have ESP. Beep, boop, beep, boop, beep, boop, beep, boop, beep, boop. ESP, we have do we do the USB to the back or to the side? Let's do USB-C here. No, wait, what? No, let's do it. Let's do the USB here. Who cares? Then we have a jumper for the power, as we did before. This is the jumper. This is USB-C. C. Then we have our nice... This is the... So this is an S3. This is the address. This is the data. These are the read, write, and whatnot. And then we have a jumper for output enable, output enable, EOE. EOE. And the rest is basically a perf board. And okay, this will be interesting because then... Oh shit. Oh. Yeah. So we can put there any logic we want. Oh, I forgot the LED. Bloop. Pink. Pink LED. Boop, 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 boop. Oh, and plenty of surface mount resistors. Here, some surface mount resistors. Bleep, bloop, 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 bleep, bleep, bloop, boop, 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 boop. Do you like that? Should we try to design that? I mean, the circuit is almost done. We just need to add some stuff. The boobies diagram. Better expose all the pins. Yeah, they're exposed. Oh, wait, they're not exposed. Uh-oh. Look done. Ship it. Okay, KiCad. Let's start KiCad. Oh, that's a template. Can we copy speichern unter? PCB. And then what? Yeah, let's do it. Wait, what? What is this? Ah. Oh no. What the? Okay, so we need the S3. ESP. I used. I think I need to include in library. Wait, what not? What? Project libraries, where is this? Are people sleeping already? Let's try. I think I killed my libraries. Killed my libraries with new version. Oh, that's not. Okay, room room. The library is a little bit annoying. I think, I mean, I had like, all the Mausers and so on have like annoying technische Daten. Where is it? KiCatch. Where is it? Snapin. S3. Oh, wait, S3. Who is that? KiCad libraries. Footprint, no. Oh yeah, socks, modules. Oh yeah, that's S3 room. Okay, that seems to be nice. Code download. License. KiCad libraries. By SA. Okay. Share like. Yeah. Oh. I put this in the same folder. Okay. Okay. Yeah, whatever. Wait, what? Oh, what? Ah. Oh, I need to rename it. Okay. Let's try again. Okay, that worked. Footprint. Project specific. Okay, let's start. Wait, is this the right project? Where's my S? Oh no. Yeah, I have this offer for Altium, I think. Yeah, for Altium for sponsorship, but I mean Altium is like expensive, isn't it? Who will be able to afford that? I need to redo this. I'm sorry. Is this symbol? Yeah, symbol. Yeah. Oh yeah, employer. Yeah. That's true. Or if you pay employees, it's also probably worth the effort. I mean, if you employer has to dig around like I'm doing all the time, then it should be easier to pay a better software for that. What is this PCB? Yes, sure. It's link.bitluni.net Discord. I think this was the link. Yeah. Oh, schematic. Let's add ESP. Let's check. Oh, nice. S3 mini room. Oh, wow. What is the difference between those two? Oh, no. Which one do I have? I need to check. I think I have the room 1. Because otherwise, I wouldn't be able to populate it if I have the wrong ones. Look at the stack of ESPs. Yeah, I'm Rambo. Look at this. This is my belt of domination. Yeah. I mean, you get you covered. Yeah, yeah, but Batman belt. Oh, these are the S3. Yeah. So I have enough S3s to make the few board. Yeah, room on 1. Yeah. Oh, yeah. There is. I found a list, I think. Oh man, what is this? This takes all the sheet. How should I supposed to work with that? Oh man. I mean, there are a few pins that are off limit, but otherwise we have, these are like already quite some pins. So let's try. No. Oh. Should we kill that? Kill it with fire. Wait, where's my S3 board? That worked. I need to use my S3 board as an example code. Yeah, I know all this. Yeah. I mean, you can still use them on your own risk. If you use it like with more pins. They did already. I think there is plenty of pins already. Where is my... was it? Yeah. I mean, you still can need SPI pins. Usually you can use them. Yeah, that's what happens usually. But if you only need like, if you use like pin 0 with high resistors in between, you can still use it. As long as it isn't like pulled low or something. I think the data sheet, not the data sheet, the module, the module data sheet for room 1 explicitly says which pins you should use and which are bootstrapping pins. Forced to use. Okay, where is my... Sona to... Wait, it should be still on my hard drive. No, did I? Oh, ESP32 code. No, that's Blink code. That's code here. Okay, here we go. Oh, look at that. I have no clue. Okay, you know what? I just copied that in my new... there must be somewhere. Can I import this? Here we go. I might not need like this footprint here. I have that one and that worked already. So this board is working and it's fine. It's... You have a solution. Oh, can you set something like really odd, not 500 millihertz? Set it to 300 millihertz or 333, so we can see something that's not synced with the clock. So it should be off. That would be nice. Yeah, it has a flip-flop. Wait, isn't that this one flip-flop fewer? Alberto, you have your own lab. Okay, I will go through all the solutions afterwards. It looks neat already. Please try. You know what? You know what? Okay, we know what the we know what the input is. Then we have a random input for enable that and we know what the output should be. How about we use like all the permutation of, let's say, 10 gates and NAND, or yeah, let's do only NAND gates, and a permutation of 50 NAND gates with the signals all around the place and brute force the solution with a random simulation, and if the output matches, or do a evolutionary algorithm that basically where the fitness level is the matching with the desired output of the signal. You need some sequential elements too. No, not sarcastic. I might have told you the story once. Works on logic? Really? So everyone was we should always do this quiz or riddle time where you just try to find out the real one. Okay, Rota, then share your output. As fun fact, someone did exactly that on FPGA. It created utterly insane results where unconnected things provided the cabinets. So, interesting thing. I was working as a coder for medical imaging stuff. And there is like you need like what I needed is I had like a direction, and like I think it was just a direction or something, and I had to calculate like roll, tilt, and like the three rotation axis to match a certain, to align a certain rotation. So I had to reverse a rotation, but there was like always some kind of gimbal lock or whatever problems you run into in 3D. And what I did in the end is just brute force, search for the right angles, and it was fast and it was good and it was used for years. Sometimes brute force is the best method, like robust method. Okay, let's take a look at this output. Meh. This shouldn't, wait, what? Okay. I mean, I solved stuff with evolutionary algorithm before, and you know what's funny, that I showed that before. Liveform needs like a brain of 16 bytes to find a way to light. So there was like simple robots with two wheels that can spin in any direction, and two light sensors. One is directional and one is intensity, basically. And the liveforms had simple code. I think it was like 16 opcodes or 8 opcodes. And so the instruction set, and then a randomized memory, and you can set the memory size. And with 16 bytes of code memory, it was enough for the liveforms to seek one light source that was placed randomly. It was seeking, like, the closer it got to the So the closer it was like to the light, it would like feed itself, similar to if it was running from a solar cell. And actually 16 bytes was the least of bytes. And you can maybe I can show it. Let me show it. I have it somewhere here. Wait. I have it here. Hey, Scott. Let me check that. I showed it before. That's the wrong code. What? I used ECMAScript ES files for that. Let me, oh no. Where is this code? Oh, here we go. Why is it so zoomed in? Oh, yeah. Oh, yeah, we played with that before, I think. Food. Oh, we have a life form. Here, this one is a seeker. I hope it survives. If it's... Oh, no. It wasn't fast enough. Oh, here is one. So that's a life form. What is the, let me check here. Evolutionary algorithm. I think I have, oh no, wait. How big is the brain? The brain is 10 10 bytes? What? Program and memory 4 bytes. Okay, that's the absolute. So this is the instruction set. It's basically read distance, read live, right, left, whatever. And okay, it's 10 bytes of program is not enough. I think with we can test, I think with 16, let me try again. With 16 we had some success. So let's do 16 and memory, I don't know, 8 bytes of memory, or let's do both 16 and see what happens. So memory is not inherited from the parents. Let me try that. Okay, we have some kind of life form that moves around, but weren't able to survive. Okay. Okay. So this is complete. This is I'm ADHD distracted, ADHD distracted. So this is like an old. Can I do like more? How many bots can I? Food, life, some kind of. Oh yeah, here we got. There is one life form that seeks the light. So the fitness is basically the thicker, the healthier it is, and the ones that are the fattest ones will survive and multiply. So that's just an evolutionary algorithm. Here is one that's almost dying. And we have like developing already. So this is like, where is it? So the life form already, we have some surviving ones that will, let's run it for a little bit. Okay, so there is a life form that seeks successfully the light source already. Look at this. Look at this. How quickly that escalates. And that basically dominates over all the other life forms that are starving to death because they don't get enough life. And it seems like always there's either a right spinning or left spinning solution to that. And these life forms are running a code. So the DNA is basically the code, which is only 16 opcodes or 16 bytes. Because some opcodes think I have multiple bytes, but one opcode could be like, or 2 bytes could be different opcodes because you can jump like an odd number of bytes or whatever. So here you go. We just witnessed how a life form was put to existence here. Oh, there is a right and left spinning life form. Look at this. Look at this. Isn't that cool? I should do a video about these experiments and maybe some better rendering for that. Look how greedy they are. There are also some mutations that basically don't move anymore. Because every time a life form is cloned and simulator, yes, it's not ants because there's no pheromones or whatever. I can show you the code that's running. So this is basically the DNA, the program. It's only 16 bytes. And they have some memory, so while they're alive, they can store some bytes, but usually that doesn't do much. This is the stack pointer, and this is the register. So they can use a register to perform set, load, store, decrement, add a constant. So this is probably 2 opcodes, 2 bytes per opcode. Subtract, then branch, if lower, if greater, if equal, and a jump. And read direction, read distance, read live. These are like the input sensors. What is this? Right, left. So these are the actuators. So left and right actuator. So this is basically the whole like body. This is the DNA. And every time a new baby is born, 1 byte is randomly, I think it's randomly changed. And this is the result. It started with a random code and in the beginning. Okay, let's run it with, let's let it run with like a huge code. 256. Maybe even bigger brain. Let's do 32 bytes of brain. Whatever they will do with that. And leave it running. So this is completely random code again. We killed the other species. And we let it live in the background while we do other stuff, okay? This is option 20. I show you what the result is later. I hope they are smart. Oh, wait a second. What? Look at this. How long? For how long is this running? Look at this. What? No. Nah, that looks like very similar every time. I hope like, but they're like, this is like 2 different races. Look at this. The one is very slow and the other one is very fast moving. Here, the slow ones didn't even arrive while the others are feeding already. So the quick one will dominate. Like piranhas. Look at this. Okay, the more brain power you have, the smarter you get, it seems. I like that. Okay, that was quicker than I expected. Okay, okay, okay. Okay, enough of this. Enough of this. We wanted to make PCBs. Okay, this is the one that I cloned. This is... Yeah. Okay, wait a second. Why is this not here? I don't know why when this started. Oh, wasn't there an edge or something? This is happening after this is already low, but we want this to be here on the first occurrence, or maybe the second. That would be like tolerant. Oh wait, this is inverted. If we invert this signal, it would be exactly what we want. Okay, yes. Yeah, PCB. Okay, this is actually not that bad. This is not that bad. Okay. Thank you, zero tolerance, null tolerance. That looks like the solution. I think we just need to invert the signal here. So it's just a knot somewhere. Metastability safe. Okay. You solved it in... Okay. It's basic. Is it the same, a similar solution to yours? Missile. Okay, we wanted PCBs. Let's do PCBs. This is our... Okay. Boof. Oh, yeah. It's in the Dropbox. Who joined shortly? I can see. Where's my chats? Here. Hey, Quindo. This was the old one. Sorry. Okay, so. I don't know where to put this properly. Okay, we have some USB stuff. This is our 3.3 volts. Is it? What is this? Wait, what is this? Enable. Oh, that's the reset button. I was wondering, what is this? And what is this? These are just switches. Basic switches, okay? So, two switches, like buttons. Here's power. This is USB. Power. Button. LED 45, and I think all the pins are capable of like output and input. Let me check that again. I think it was in read the docs. Nope. Okay, here we go. Here you go. Type IoT, it shows everything. So this is the data sheet for the room module, and it says what's bootstrapping, strapping pins. 4 strapping pins, just avoid them. I think I used 45 as an LED or something. Yeah. So GPIO blah blah blah. So this is basically what we. Yeah, they're very simple, very simple. So did I show the other one? Look at this. This is my dev board, my S3 dev board, and it has 2 buttons. So you only need USB 3.3 volts. And what is that? Oh yeah, this is also USB. So no, USB-C. You can do whatever you like with that. LED, nothing else. This is it. This is it. You need like to, I think, keep it pressed when you plug in. I don't know, it works like that. I don't know. That's 10 microfarad on input and 100 at the output. I think this was spec of the LDO. So I don't care. I did it like that. It worked like that. Larger cap on. Yeah. So let's leave it. Leave it. And try to get all the addresses. Okay, so what we need is we need this instead of that and that. And we need yeah, OEA. See, chip enable, then we don't need, oh, there is no ground connected, okay. Maybe I should move that a little bit. It's all over the place, but it makes sense, no worries. 5 volts, 5 volts. Address. We can use a direction pin for that. What? We can monitor the address in real time. Oh, which data sheet? Of the ESP? Oh, okay. I think, I don't know if I even use this specific LDO because I have like a stock of LCSC LDOs. So that might be not even the right one. I must check that. It's not important right now. I be doing only the schematic today. The routing, that takes long. We are almost at 12 o'clock. So I will just change everything here. Plop. Okay, noted. Boop. I use B for that. This was only for convenience to use it in this direction. D. It lined up better. Wait, B. Or do we do it like that? Yeah. And we need new signal names. The ESP. ESP A11. ESP ESP ESP. Here we go, and all that again. I mean, going directly for a PCB with an untested design is always scary. But I don't want to deal with the shifter anymore because that takes so much time to shift the data, I mean the address. Yeah, we don't need serial, we don't need serial clock, we don't need this, we don't need clock, that was it. BA5 reset. Okay. $22 microfarads. Wow, that's a lot. So you have to like put a huge physical one on that or what? Oh, okay. So this is tier 0. I think we will optimize later. Tier 1. And I hope, or should we call it tier R for address? And this should be tier D. Tier D and okay. Okay. How do we assign it? So DNDP, this is USB. We can use everything except 0 and 3. What does 3 do in this case? It would be the best to have them shiftable as a whole byte. So is there a sequential 16 bits somewhere? I don't think so, because this is like we have 4 bits, 435, and then no. This is the same. 14, 9, 8, 7654. This is the closest we get. I need to find an assignment for that. Five, six, 7, 8, 8, 9, 10. It's unfortunate. And 12, 13, 14. Yeah, that's all we get. And 15. Oh yeah, we have 15. 15. 16. We're almost there. 17, 18, 19, please. No! 1 bit! No! 1 bit! No, why? Why? Espresso, why did you do this? I need this. Oh, we start at 3, but this is, let me read again. 1, 3. Is 3 even, is 3 even available here? No, I don't think it's available at the room. Is it available at the room? It is here. No. Okay, don't care. Oh, it's eFuse. Guten Tag. Big Bang, one of the G. Good night, Rota. I think we can use the GP, not. Wait, JTAG. JTAG, I really don't care about JTAG here. We would use high anyways. I mean, we could pull it high. No, we can pull it high very weakly if we want to set this. Otherwise, we will check. The output enable will be floating anyways. I don't think that's a problem to use GPIO 3. This is the most important one. GPIO, pull down, download boot. SPI voltage. So 45 is important. 0 is important. it does some pull down, which is also which can be ignored. So if we shift everything to start at 3, we can even start at 1 if there is any. 1, 2, 3. Yeah, let's do that. Three. Wait, flip this. Okay, 1, 2. We just have to shift by 1 and then the address, and we can basically, I need to X that, X. Use everything but pin 0. And even pin 0 could be, I might even be able to use pin 0 here as PI boot. Download boot. Nah, I leave it. I leave it. I keep it clean. 2, 3. 4. 5, 6. 7, 8. 9, 10, 11. Okay. I have an order. For that. Oops. Ten, 11, and now I need 8 more bits, which are these here, and the other ones that are randomly assigned. Okay, let's get 8 more bits that are consecutive here. Doop, 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 doop. How do I can delete these here? Dip. Oops. Okay, address is covered. Now we need to do the data, which is 1, 2, 3, random, 14, 15. When does it start? These are DNDP. Okay, these are 4. I need 4. 12. Ah, fool. These are not consecutive. 5, 6, 7, 8, 9. here. Wait. 5, 6, 7, 8, 9. 8 bits. But it's a different register. It's a different register. If we can fit everything in like consecutively in one register, we could write faster. Because then we can set the data and the address at the same time, push it out, and do next. Imagine we can do like a FIFO or an array of like addresses and data bytes that are stored in an array and then basically sequentially pushed out. That would be cool. Yeah, I know. But FPGA doesn't have Wi-Fi. RP2040 doesn't have enough pins. Does it? Yeah, profit. But then you can use also, okay, yeah. No. We are working in megahertz range. There is no way. This is what we got rid of. The shift registers here. This is what we just get rid of to be able to write faster. Megahertz range. Why did they do this? Yeah. FPGAs everywhere. Yeah, I know. I will. Once I went FPGA, I will never return. This is tempting to put it there. €20. Yeah. Then I wait. What is the LED? The status LED. Status LED is 45. Okay, so I can use 46 and 45. Wait, 14, 18, 19. Wait a minute. Huh? No. 10. What did I do here? What is happening here? I'm confused now. No. What? 10, 11, 12. What is going on here? No. 8, 7, 7. Okay, it's always -1. So 8, 2, 10, 11, 12, 14, 15, 16. Okay, now there is no place. There is no place to do data as well here. '17, 18, then we have like these ones. Then we have a random here, random there. Of F this, I put this here and that's it. 35 to 42. Let's check. 35. SPIO, whatever. 6, 7, 9, 4, pop, 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 pop. And B is PS RAM. Yeah, we are not using PS RAM here. Okay. So we have enabled I/O. CC1, CC2, this belongs to the USB here. This is USB stuff. VBus, DP, whatever, whatever, whatever. Power. That's 22 micro, 10 micro. Let's do 10 micro for now, even though they can suggest whatever they want. Okay, what are we missing still? We have, these are here optional, but they're cool to have. We are almost there with the schematic though. So, it looks like we have like only a few left. Here, these are the restrictions. Huh? Where is the rest? Oh yeah. 40, it's all input, output. Input, output, input, output, input, output. There is not much, only enable is input and power pins. It's so cool. Super cool. Okay, we have still enough pins. What's interesting is we need oh yeah, that's e-reset, which I added after the fact. Do we have output enable A? Oh, Johnny, thank you for the donation. Output enable data. We have this. This is now like split, but I don't know if we want to do this. So we might combine these two. Oh yeah. Here you go. www. It's HTTP. www. Yeah, but Eagle isn't free, isn't it? Okay, 0 is very, very important. Pull down, download, boot, 64. Which pins did I use for the buttons? 0 and enable. Okay, 0 and enable, but what is with 64? Don't care boot mode. SPI boot. Yeah, it does. Oh, oh, that looks like pain. I think I will leave 46 open here. Yeah. Okay, so we have 2 direction pins that might be combinable. What is... Good night, Dave. Reset. Okay, this is optional. What is DMD? Oh, DMR, DMA. Oh, that's important. These two are important. Okay, we have 5 pins. And we have 1, 2, 3. Oh no, but we want these. Wait. Wait. What's with RX and TX? Can we use them as seven and 6? Huh. Look at that. Yeah, I think I can put jumpers there for the optional signals. Yeah, because I don't use RX and TX anyways. So this is basically, I can put these two here with a jumper, which is cool already, or I can use them as RX and TX for whatever reason, because I'm using USB anyways. Yeah. And then we just use one output enable, no extra, one direction pin, no extra, and hope we don't get timing issues. No, I use USB. Wait. DMA, ADMD. This was randomly attached or what? I can't find this. DMA. I have no clue where this is attached. So let's just not do it. Reset is... That's okay. Oops. Ah! Yeah, of course, the S3, S2, CDC. So direction, where do I put the direction? Oh yeah, that's... Okay. EDMA S21. Uh-oh. Output enabled 47, that sounds scary. Read write. You know what? Move it here. Here we go. Fully stuffed. We need to do something like that. But this will be, oh yeah, and all this crap here needs to be figured out, because I think there are still some issues. I need to oscilloscope that and change the values. I think we are done. So good night, and I will basically conclude this stream as well. We did some FPGA stuff. We did some artificial intelligence stuff like evolutionary algorithms. We did some a nice riddle. Wait, what is this? Oh yeah, that's needed for as pull down here. I might want to put it here. Yeah. Oops. And we did some PCB design. No, schematic, no PCB design, sorry. But with this tidy up and we need still to figure out. There are probably other streams that are interesting. You have popcorn, Ray. Okay, here we go. Good night. And I don't think I will use the connectors. I will do new connectors. So still some connectors to make, but fingers crossed that could work with the ESP32S3 without shift registers. We need some extra logic here. And what? What kind of cipher is that? Single clock logic. We didn't manage it. Design ESP-S3 board, almost. So only one thing crossed. Option 22. Thank you everyone for watching. I hope you enjoyed this stream so far, and I mean the complete stream. And it was cool. And yeah, I see you next time. Bye. Where's cue the music? Cue the music. Is there a music? Media source. Here. Is the music playing? Yes. Okay, but I will need the rest first. So I will take a look at that. See you next time. Bye. How do I kill the stream? Kill it with fire. I don't know how to end this. Here. Bye bye. Good night.